So I will seek to speak with clarity. Sorry, my Spanish is a little rusty. But we start with a picture from my childhood. This is where I am from, and this is perhaps why I got interested in acid rain. This is along Lake Michigan in Indiana. The city of Valparaiso is close to here in Indiana, not Chile. The city of Chicago is across the lake. And this is famous for its industry around the lake. There's the city of Gary, Indiana, sadly known for its murder rate, not always its industry. And growing up, you'd play on the beach and see the acid rain being created. So perhaps this is how I got my interest in air quality. I show it not only to introduce myself, but this is also one of the hot spots of acid rain in the moment in the United States. And it's great to come here and to share the work we've done. And we will finish to talk about future collaborations between UNAM and our university. But before I begin, I have to send my condolences and a tribute to Dr. Bravo. I know he passed away earlier this year, so my sincere condolences. He came to several of our meetings. This was a little mucho frío, a little cold there, one of our annual meetings in Park City in Utah. My favorite memory of him is he talked maybe twice at our meetings, and he would always start en español, and somebody would have to shout, "Anglais, Anglais, Herr Bravo." So in tribute to him, I will begin in Spanish. Descansa en paz, querido amigo, se te extraña. You are missed, dear friend, rest in peace. He had worked greatly with our program to increase our collaboration. So this is a map showing pollution sources in the United States. I am from here, the Illinois State Water Survey. We are on the campus of the University of Illinois. Chicago is up here. The picture I showed you is just east of Chicago. And nicely, I flew from Illinois at your invitation, thank you, making a stop in Dallas, and came here to UNAM. And the reason I'm going to show this is the only message you need to learn today is that we may have some artificial borders, if you will, this yellow line where we can pretend to stop economies, stop politics, perhaps stop people. I will not comment on that today. But we cannot stop the air. The air knows no boundaries. And it behooves us to better understand the air we share in North America. And that is the only message that you need to take home today. So, air knows no borders. And this is a nice recent Google Earth series that put out by the U.S. Environmental Protection Agencies that shows top sulfur dioxide emission sources. And in dark blue, you can see is electrical generation. We have a lot down along the border that supports the industry. And you know, we have this border, and through the air we can exchange gifts with each other. So we send you our air, maybe with a little additive, and likewise with the industry along Mexico. So it behooves us to better understand these areas in the United States and also along the Gulf of Mexico, where we share this major water body. So that is the message today. We need to share and be common stewards of the air quality of North America. I bring greetings from my laboratory. As Dr. Sosa introduced, I am the director of the Central Analytical Laboratory. Here are my people. So I am the director. Lee supervises my laboratory for the staff. Our programmer is in the back there. So we have a wonderful staff, lots of great experience in there. We are on the campus of the University of Illinois within an institute called the Prairie Research Institute, but we are on campus at the university in Champaign. Just some quick pictures of our laboratory, and sorry if some of this is boring to those that came yesterday, but we run ion chromatography. We right now have a Thermo Fisher Dionex system, inductively coupled plasma. We have a state-of-the-art Agilent system that was just introduced, and we run colorimetry. And I'll come back and talk more later. But, you know, laboratories around the world look the same. I got to tour upstairs. Thank you for the tour. And you can see they look very much the same wherever you are. We also do air quality measurements. This should show you why vacation in Champaign, Illinois is not a good idea, because there's nothing to see. We have no mountains. These are not mountains, those are trees. It is mostly agricultural land. And we do air quality measurements for the U.S. Environmental Protection Agency. So we have filter pack and then air inlets at 10 meters. We run the analyzers for the criteria air pollutants, which I will talk about in a minute. But of the 6 criteria air pollutants, we measure 5 of them, and that would be sulfur dioxide, nitrogen oxides, carbon monoxide, ozone, particulate matter, and then lead we do not measure. Since the United States has banned leaded gasoline, we are no longer routinely required to measure it. So for that introduction of me and where I'm from, let me introduce today's talk. So I'm going to begin by talking about air pollution regulations in the United States and air pollutant emission trends and how those have affected acid rain trends. I will introduce our program, the National Atmospheric Deposition Program, or NADP. I will show some trends in our data, and then, time permitting, I will attempt to not go too quickly, but we have some special studies that I think would be of interest, especially towards future collaboration. So I will introduce the National Ambient Air Quality Standards, or NAAQS, as we say. There are 6 of them for the criteria pollutants: carbon monoxide, lead, nitrogen dioxide, ozone, particulates, so both very fine particulate matter. This is smaller than 2.5 microns, and then PM10 is smaller than 10 microns, and sulfur dioxide. And then for the government sends 2 levels of standards. There are primary standards and secondary standards. The primary standards protect human health. The secondary standards are for general welfare of the population. So for example, today we're going to be focusing on acid rain species, nitrogen dioxide, and sulfur dioxide, and we'll see how these interact and form acid rain and acidic deposition. So you can go to the website. EPA publishes the 6 NAAQS, and just to bring one in particular, for nitrogen dioxide, studies have shown the primary standard is 1 hour, so it is safe for affected populations to breathe 100 parts per billion for 1 hour, so these would be people with asthma at risk. And then a secondary standard of 1 year, so a longer averaging at 53 parts per billion. And if you were in one of my classes, we would be looking at some of this data and figuring out how these averages are calculated. So trends in U.S. emissions. This is data provided by the U.S. EPA of emissions in teragrams. Sulfur dioxide is shown in red, nitrogen oxides in blue, and this is literally how the data comes. It's every 5 years, 1970 to 1985, and from 1990 thereafter, you can get annual data on the nation basis. And if you look deeper, you can also get state and county level data. So there are various regulations in effect, and to translate the acronyms, CAAA is Clean Air Act Amendments, and CAIR is Clean Air Interstate Rule. The only other political statement I will make today is nobody knows future regulations for air quality in the United States, so that is still in question of whether these trends will continue. Before the Trump administration, there were further regulations to come into effect. Everything is in question, much like the world. So a little bit about atmospheric deposition. I think this audience knows it very well, but in general terms, we take an emission source, may it be a power plant, it gives off emissions, or a vehicle. These go into the atmosphere where they can react with other chemicals and with sunlight in photochemical reactions. And then, as I like to say, what goes up must come down. So the pollutants come back in the aqueous phase as precipitation, and in the gas and particulate phase as aerosol particles and gases. And if we know how much it rained, or we can use some computer models to figure out how fast the gases come down, we can calculate the net deposition. And I will not talk much about environmental effects today, but it can affect cultural resources, water bodies, and indirectly affect human health. And what we focus on is the wet deposition. There are other groups in the United States we partner with to do the dry deposition. So this is our network of all active stations currently operating, and you can see the color of the dot shows site longevity. So 1 year from now, in July 2018, we will be celebrating our 40th birthday. Our first network was founded in 1978, and you can see how we've grown. Not only do we have long-term sites, but we have a number of new sites, and you can see we have a wide geographic distribution across America, Canada. We even have stations in Taiwan, Puerto Rico, Virgin Islands, Argentina, not shown, and then the US states of Alaska and Hawaii. We did operate 2 stations in Mexico, which I will talk about later. So just briefly, I will be using acronyms, but to introduce them, our largest network, the National Trends Network, was founded in 1978 to look at acid rain and acidic deposition. Our Mercury Deposition Network looked at mercury and precipitation, and it was founded in 1995. A small research network collects event samples, was founded in 1992. We look at ambient mercury in the gas phase since 2009, and ammonia monitoring network since 2007. And again, apologies for those that were here yesterday. Some of this may be a repeat. But my laboratory, my group, analyzes samples from the 3 networks with a star. These samples go to a contract laboratory. And in total, we are a busy laboratory. We process approximately 18,000 samples a year from these 3 networks from over 300 unique locations. So where does all the money come from? We do not choose our stations. In fact, agencies come to us and provide the funding. We operate as a cooperative research network. So we have over 100 agencies contributing funds and support for this, including U.S. federal agencies, primarily the U.S. Geological Survey, the U.S. Environmental Protection Agency, NOAA, that's the National Oceanic and Atmospheric Administration, the National Park Service, and others, through the U.S. Department of Agriculture. We have individual U.S. states and Canadian provinces. We have indigenous nations, tribal organizations funding our stations. And then many of our sites are located at universities, so we have in-kind support from universities. And then we also have partners in other organizations, including BP, EPRI, that's the Electric Power Research Institute, and Environment and Climate Change Canada. So they fund 1 or more individual stations. Just briefly, I want to talk about our networks and our analyses before I talk about trends in the data. So the National Trends Network looks at the major ions, cations, anions, pH, and conductivity. We have 263 sites, plus 2 we operate for quality assurance, and we've collected over 430,000 samples since 1978. And all this data is freely available on our website. For agreeing to be a partner in our program, you must agree that the data are shared at no cost. The research network is AIRMON, Atmospheric Integrated Research Monitoring Network. It's essentially the same as this network, but we collect samples daily and we refrigerate them, which better preserves nutrients. It's expensive, so we only operate 6 sites. A little bit more about our National Trends Network. So we do weekly wet deposition sampling from a wet-dry collector. We only collect the wet deposition currently. We have a recording rain gauge that many of them are on telemetry, so we can real-time have 15-minute data. And then for chemical analysis, we look at the acid rain species of sulfate, nitrate, chloride, and bromide, the base species of calcium, magnesium, potassium, and sodium, nutrients of ammonium and orthophosphate, and then, of course, pH and specific conductivity. And here are some, this is my boring site in Illinois, something more scenic from a national park. This is in the U.S. state of Nevada, Great Basin National Park. About 20% of our stations are off-grid, in other words, no electricity, so they can run on solar power. That's no problem. With our samples and our precipitation record, we can know exactly when it rained, and we can do a back trajectory analysis. So this would tell us where it rained here in Ithaca, New York. That's the city with the black star. We can see that the storm system tracked over the Midwest. So having the records of precipitation and sample chemistry lets us do some predictive modeling. And at the very end, I'll show some special studies where this came into use, where we did some fallout of the Fukushima disaster and the Gulf oil disaster, Deepwater Horizon. A bit more about our networks. Our Mercury Deposition Network measures mercury and methylmercury concentrations. We have right now 100 sites and close to 90,000 samples that have operated since 1996. Our Mercury Monitoring Network looks at gas phase speciated mercury. We have 23 sites since 2006. And here are some pictures of the MDN site. This is to greet our friends in Canada. This is Kejimkujik National Park in the Canadian province of Nova Scotia. It is a very remote site, but it is influenced by air masses coming across the United States. So they have a wet deposition collector. It's enclosed because it freezes in winter, so it actually gets heated because the glassware would break. And then they have a recording rain gauge with a windshield for snow capture. This is a map showing the mercury wet deposition in 2015. This is the site I just showed you in Kejimkujik. So the map shows data from our program, but integrated over the year. So we take the mercury concentration in individual samples and multiply it by the amount it rained, and we get a mass flux. And green is lower, red is higher. And you can see where the Gulf of Mexico becomes a keen concern for mercury deposition. The concentrations are relatively uniform, but because it rains so much more in the Gulf states of the United States, we see much higher mercury deposition. And you can also see the Puerto Rico is also one of the higher stations. And again, all this data is available online for free. You can get the maps and download and use them. As I mentioned, there were 2 NADP stations that operated here in Mexico. One in the state of Hidalgo that operated from October 2004 through November 2005 on the Gulf of Mexico, or relatively close. And Puerto Angel in the state of Oaxaca that operated from September 2004 and October 2005. And those stations are no longer running. I just did, since we're here in Mexico, a quick data comparison. If you took all samples from the year 2005 and plot a box plot, so this is median, 25th percentile, 75th percentile, minimum and maximum, and you expand it out, you can see for the 2 stations, Hidalgo's in red, Oaxaca in green. Hidalgo, the median is about the same as all stations. Oaxaca had a higher median concentration, but a lower overall mean. And this is more closely seen if you line up all our stations from cleanest to dirtiest. So this is a cumulative frequency distribution. So these are the cleanest sites, the dirtiest sites. Oaxaca would fall in the lower third, and Hidalgo, just below the 50th percentile of all stations operating in 2005. Switching to gaseous phase mercury, it is by a continuous analyzer. We use Tecran instruments that measure gaseous oxidized mercury and particulate-bound mercury. Particulate-bound mercury is in green, gaseous oxidized mercury in red, and you can see the classification. These are urban stations, stations that are influenced by urban areas, and then remote stations. So these are box plots, and then the little or big dots above represent outliers above a concentration of 40 picograms per cubic meter of air. And you can see our urban sites definitely have more gaseous oxidized mercury, as does our station, which we operate in Taiwan. The last introduction to our networks, it is our ammonia monitoring network, and this uses inexpensive passive samplers. I brought one with to show. And it has a gaseous diffusion membrane that controls the diffusion of the gas, and then there's a central sorbent core that traps the pollutants. And we use these for measuring ammonia, but you can also use them for hydrochloric acid, sulfur dioxide, nitrogen oxides. And they're really neat because you can put them out. You just hang them in a rain shelter, and right now we have 100 stations doing these. So we have, we're working on 2016 data, so this is our last complete set for 2015, and you can see high ammonia concentration in the agricultural region of the United States, which is in the Midwest here. So this is where I am from, Champaign, and then the agricultural area, and the data are very good and consistent. And this is about the only data set we have in the United States of ammonia concentrations. We've also used these for transect studies across cities. This is our city. There's Champaign and Urbana. The campus is in the middle. That's why it's Urbana-Champaign. And we've done air quality transects across the city, and you see variability. So we start in the farms and go towards the city. We'll see higher concentrations where the students live, and even more. This is an industrial park near several interstates and railroads out here. So even over this area, we see quite a difference. And it's completely flat. So this is all agriculture and a university city. So I've given an introduction. Now I want to show some trends in our data. And the first question that we have almost 40 years later is, okay, why are we still worried about acid rain? And acid rain, this is the last complete data set we have for 2015. We generally classify acid rain having a pH less than 5.1. That's this red line here. I will tell you why in a minute. And you can see this map was much different many years ago, but we have generally pHs less than 5 in the eastern part of the United States and higher pHs in the western, so indicating less acid rain. And then our station in Illinois is pretty much the dividing line here. I now have to apologize. I'm an American. America is not an island, I realize that. So excuse me that Canada is missing, and so is Mexico. So please excuse the island of the United States. And you can see the stations not included here. And again, all these are available on our website. So why do we say acid rain is less than 5.1? We say we have that to represent human-induced pollution. And the reason is we know purified water is naturally acidic due to the carbon dioxide in the air. Carbon dioxide gas dissolves in water, forming a weak carbonic acid. So with our current levels of carbon dioxide in the atmosphere, the pH is about 5.6. As a side note, since we are 40 years old, we actually have had to adjust our assumed concentration of carbon dioxide for our ion balance concentrations, because as you may know, carbon dioxide continues to increase in the atmosphere. So we set the level below 5.6 to represent naturally occurring acidic species that can reduce the acidity of rain, and that would be sea salt aerosols with sulfate and naturally occurring organic acids. And if you look at just a quick time trend, these are box plots, so these are the same 152 stations. You can see in 1985, the median pH was less than 5.1, so more than half of our samples were acid rain, and now it's only 25%, so a radical switch in, what is that, some 30 years. Yeah. Okay, so now I'm going to talk a bit about how acid rain influences acidic precipitation from the sulfur dioxide. And I call on my friend the raindrop. So he or she is getting acidified with sulfur dioxide gas. And the relevant reactions are the sulfur dioxide gas dissolves into water and disassociates to form a hydrogen ion and hydrogen sulfite. And then hydrogen sulfite can further dissociate to form sulfite ion. That oxidation, what we actually measure is sulfate, because the sulfite readily oxidizes in the atmosphere. There's multiple pathways. The easiest one for me to show is by ozone. So sulfite gets oxidized by ozone to form sulfate ion. And there's other species that can oxidize it there. Hydrogen peroxide, OH radicals, nitrogen oxides, formaldehyde, iron, and manganese. You can pick up any good atmospheric chemistry textbook and find the reactions for those. So my poor little raindrop is getting acidified by SO2 gas to form sulfate. Now let's see what has happened. So I am going to be showing an animated movie of sulfate wet deposition trends, and it's going to be a moving average from 1985 to 2013. And the scale you'll see is green is low, red is high, and the units are kilograms per hectare of sulfate deposition. Just a note, the precipitation is actually augmented with some modeled data to show better some of the mountainous regions of the United States. So I'm going to start the animation. This is 1985. These are the highest concentrations of sulfate in the United States. The Clean Air Act amendment started in 1990, and we make it disappear. Hopefully. So you can see the years down here as we move forward. And we see, remember Indiana Dunes? I showed it because it's still a hot spot. So one asks, is 1986 better or 2012? So you can see dramatically the time trend. These are all the same stations, so we did not add or subtract stations. These are the same stations operating over this period. We integrate our data with that of Canada. There is what's called the National Atmospheric Chemistry Set that's run by Environment Canada, we share data, and you can very nicely see we can map. This is deposition of sulfate in the year 1990 across the border. It would be wonderful if we could increase collaboration so we could go south a bit too, to complete the map of North America. I'm going to show nitrate now, and we have nitrogen dioxide, again my little raindrop, forming nitric acid that eventually forms the nitrate ion. So this occurs, the major pathway is in the gaseous phase. We have nitrogen dioxide reacting with an OH, that's a hydroxyl radical, and this is what's called a three-body reaction. So this would be, often it's water vapor, it adds energy to help in the dissociation. So the nitrogen dioxide picks up one of the O's to form nitric acid, reacts with the OH to form nitric acid, HNO3, and then that can dissolve into water to form nitrate ion. So again, similar to the sulfate trend, we can see 3-year running averages. Green is good, red is not so good. Remember, the Clean Air Act amendments came into effect in 1990. And again, nitrate disappears. And we can ask, this is 1986, high concentration of industry and populations. Oops, and 2012, greatly reduced. Often I get questions of how come we don't see California, because certainly California is a large industrial state. I believe it is the 6th largest economy in the world alone as a state. And the primary reason is, well, there's twofold. You have a lot of ocean influence clean air coming in, blowing the pollution inward, and also it's dry, so we have dry deposition there and not wet deposition. But we do have sites in the state of California. Now I'm going to tell a different story. We're going to look at ammonia gas, and my little raindrop is turning blue now because instead of turning acid, he is becoming basic. Ammonia gas dissolves into water and disassociates at the prevalent pHs we measure to form ammonium ion. And ammonia, here I'm going to show concentration trends, not deposition. So it's the same scale, 3-year running average, but it will look a little different because we don't have the modeled precipitation. So this is 1985, nice and green, beautiful fields. And we can see, coincident with the decrease in acid rain, a large increase of ammonia. And remember again, this is the agricultural area of the United States. So we go from 1985, verde, 2012, rosa. So we go from green to red, primarily in the agricultural regions of the United States. And that was really the motivation because there was not a good data set of ammonia. It is not regulated, and it's also politically sensitive because it's from agriculture. And so there are concerns, but we also have a lot of cultural resources here. The state of Colorado, much more beautiful than Illinois, but Rocky Mountain National Park, many national parks out there. So there is a concern. But it was the motivation for our ammonia monitoring network because we didn't have the data. And this graphic is just a Google Earth image. The background map is the ammonium ion and precipitation from 2015, and the dots represent gaseous ammonia from the same year. And you can see the dots where they are red fairly well overlaps areas where we also had high ammonium ion and precipitation. So our other atmospheric studies, that was an introduction to the NADP. Now I'm going to talk about projects we've done. Since we have the infrastructure of a large international network, we have done many special studies using our infrastructure. Nuestros otros estudios atmosféricos. The first one that comes to mind was the Chernobyl disaster in 1986. This is what our network looked like. We collected samples and sent them to a government research lab to assess the extent of the deposition from the Chernobyl disaster. That was before I worked in the laboratory. More recently, during my career, we were called upon to assess the impact of Fukushima that happened in March 2011. As you might recall, the earthquake epicenter was off the coast of Japan and affected the Fukushima Daiichi nuclear power plant. And this is before and after. These are the nuclear reactors. And the earthquake and the resulting tsunami destroyed the reactors, resulting in a net emission of radioactive material into the atmosphere. So we were called upon to provide samples. We took our bulk water samples and also the filters of our samples and sent them off to a government laboratory in Denver, Colorado, operated by the U.S. Geological Survey. And I got to visit. It really is agua azul. It looks just like this. It's cool and scary as you're standing there. But they have a facility for their geophysical institute there to assess radioactive isotopes. This is what they actually use for the analysis to excite the ions. We didn't need that because we were already having radioactive material, but we took advantage of their gamma ray spectrometers. So this is lead bricks. We had very, very low counts, so we were counting like 48 hours a time, but we had to shield from natural radiation, and this was also cooled with liquid nitrogen. We measured many of the most noxious or hazardous radioactive materials have a half-life of about a week. It took about a week for the storm systems to track over the United States. So we were able to look at iodine-131, that's a radioactive isotope, cesium-134, and cesium-137. In the interest of time, I'm just going to show the cesium-137 map. And what's interesting is how it banded across the United States. So as expected, we had a radioactive deposition along the West Coast. The units, the larger the dot is the larger the activity, and the units are picocuries per liter. We missed some sites. There was a band over the Rocky Mountains. Again, missed some sites and a band over the Midwest. So you could see the diffusion. And I just ran some high-split models, some simple modeling, and you also saw it like fanning out through the trajectory analysis. We published this, it was the lead story in Environmental Science and Technology later that year, so we have an ES&T publication on this. We also did measurements. These are the Aleutian Islands in Alaska, and we were also able to detect radioactive isotopes there as well. And the other maps are in our full publication, the cesium-134 and iodine-131, but we had the most detections of cesium-137. It's also one of the most stable species in terms of longest half-life. Turning to another story, another use of our network, we responded to the Deepwater Horizon disaster in 2010. You might recall, I think it was BP, they had their oil well that exploded and large emissions of pollutants into the atmosphere, and we were called upon to assess the impact as part of the legal case with the U.S. Environmental Protection Agency. And we measured the species, the sulfate, nitrate, ammonium, and mercury as the likely resulting species of this disaster. So again, I did some forward trajectory analysis. This black star is where the explosion was, right off the U.S. state of Louisiana, Mississippi, and Alabama. And you could see it tracked inward. And this is also where we have a high density of our stations along the Gulf Coast. So the well was here, so the pollutant tracked right over many of our stations. The blue squares are our acid rain sites, and the red circles are the mercury deposition sites. And you can see I did a comparison of the years, the annual box plots for 2007, 2008, 2009, 2010, and you can see when we looked back, 2010 was an anomalous year in terms of the wet deposition of sulfate, nitrate, and mercury. What's interesting about this study is this is also a very polluted part of the United States. We have a lot of petrochemical industry here. So interestingly enough, we didn't see any samples that looked elevated. In fact, if you just laid the data out, you'd think the weeks after the disaster you'd see it. but there is generally a lot of background pollution in this part of the United States, which again reinforces the message. Our shared border of the Gulf of Mexico is something that it behooves us to study the impacts of our industries in the region. And one of our other initiatives we're looking at is, we're calling it City Dep. Most of our stations were established in rural and remote areas, national parks, but that is not where the people live. So we have a new initiative to look at urban deposition sampling, not only for atmospheric wet deposition and its impact on air quality and parks, but dust and dry fall and allergia, so pollens and aeroallergens. So this is our most dense site. This isn't Mexico City, but this is the city of New York, in the quarter of the Bronx. We have some rooftop sampling of air quality, and you can see our station is at one of the botanical gardens in the city of New York. So we're doing monitoring right there. And as I mentioned, not only are we interested in doing acid rain, but we're also looking at doing pollen and aeroallergens. This is actually my arm. I suffer terribly from allergies. They make me miserable. So I had my doctor take my picture because they actually shoot you in your arm. And I'm most allergic to ragweed. So right now you go to the doctor's office and they say these are the seasons for the allergies. But if we had more real-time data, we could tell where aeroallergens are in the United States. The current sampling in our national network is, I know you have a Burkhardt sampler here, but the conventional sampling in the United States is a rotorod sampler. It just spins a little rod, collects pollen, and then you use a microscope to analyze it. We've teamed up with the University of Maine in their Climate Change Institute to analyze our samples because perhaps much like your laboratory here, all samples get analyzed and then we simply throw the filter away. But we were able to send it to the University of Maine where they washed the filters and did a microscope analysis to identify pollens, Pinus, Populus, Alnus, and Acer rubrum. These are common allergies and allergens that you can find. They've also worked to automate this so a liquid sample could be put in and then so it's not quite so time consuming. We have a full report posted to a blog if you're interested in the preliminary data for that. And then this is how the network would be expanded. The black is from our National Allergy Bureau. These are operated by doctors and hospitals using the conventional rotorod sampler, and the red is our network. So we could greatly expand at very little cost aeroallergen monitoring in the United States by incorporating this into our method. So that's that. And I will finish. I didn't want to go too long. We're about quarter till. I want to have plenty of time for questions and discussion. So now let's look at future collaborations. Futura collaboración between UNAM and CIMAT and the NADP and the University of Illinois. This is some of the historic data from your laboratory here, looking at Mexico City wet deposition over time, in particular in pH, and then data from our program that we looked at earlier. And how can we integrate our data sets, much like we do with Canada, to have an integrated picture of air quality and the effects of atmospheric deposition in North America. And I'm very glad to be invited here so that we can talk about this collaboration. And with that, I know we have plenty of time for questions, but we'll finish with preguntas.
Thank you very much, Chris. It was very nice talk. Now the answer the questions. Tenemos tiempo, por favor, para preguntas. Pueden hacerlas en inglés o en español. Your name.
Muchas gracias por la conferencia muy interesante. Le quería preguntar acerca del convenio de Minamata. México signó el convenio de Minamata y se comprometió a reducir las emisiones de mercurio. Por lo que usted demostró en su presentación, Estados Unidos ya no tiene ese problema, y ustedes ya van muy avanzados en el control, en la medición del mercurio. ¿Qué recomendaciones haría para que en México se pueda llegar a tal meta de reducir las emisiones de acuerdo a lo que se comprometió México en el convenio de Minamata?
Okay. Well, and I should thank the translator for the excellent job, too. I understood the question to be about the Minamata Agreement and the U.S. involvement. I will be honest, Mercury is not my area. I know there's been ongoing negotiations with the U.S. as a partner to the Minamata Agreement. I believe you also asked what the regulation would be for the practical impact in Mexico to reduce mercury deposition. I know that was many years ago the motivation of establishing the two sites in Hidalgo and Oaxaca. Sadly, they weren't able to continue. But from the standpoint of the United States, most of the regulation has focused on, well, this is going to take too long to get back. Most of the regulation has focused on power plants and direct injection of carbon, activated carbon into the power plant. Now, what's interesting is, in general, the acid rain has also been solved by economics, because right now, natural gas is being burned more for a power source than coal, and I believe natural gas has also a lower mercury. So if we're just looking at the power sector, power production, I know mercury in general has been trailing off, but I believe in Mexico, or from my limited understanding, there's also concern from industry, cement kilns and the like. That I don't know much about, but there's certainly control technologies available, most promising with activated carbon and in wet scrubbers. And I'm not sure I adequately answered your question, but I appreciate it.
Thanks, Chris. ¿Otras preguntas, por favor? Luis, por favor.
Hi, thank you for the nice presentation. So it's pretty good to see how you were able to reduce the concentration of the pollutants. And given that, based on the presentation that we had yesterday, those pollutants, they must serve as a catalyst for rain formation, right? So had you checked, or anyone, the trends or any correlation between the levels of precipitation or the precipitation patterns compared to this reduction of pollutants?
That is an excellent idea. There were some historic studies that we did at the University of Illinois. We had a dense rain gauge network. This is about where the city of St. Louis is, right? Am I pointing correctly? So we did intensive studies 20 years ago to look at the effects of pollution from St. Louis on rainfall. And you are correct. We did indeed see enhanced precipitation from the pollution there. Right now, no, we're not doing any ongoing studies. We more see temporal trends in climate. So, for example, much of the United States, maybe you've heard, is undergoing drought, and that has had a direct influence on the chemistry. So in drier regions, we tend to see more cations like calcium, magnesium, and potassium. But no, we have not looked at a direct impact to correlate precipitation intensity with chemistry. But because our data is free and on the internet, we can welcome anyone to do that study, and we would support it, of course.
¿Más preguntas, por favor? Oscar?
Hello, thanks for the talking. It was very interesting, especially that decrease in concentration of SO4 and NO3, because both are related with fuels. And I suppose that decrease is based on changes on energy programs or regulations.
Yes.
And the question is a little more political, because now you have a president that has pushed the industry to use anything they need to increase the economy. So maybe you are going to back to maybe concentrations larger than now, I suppose. I don't know.
Pergunta interessante. Interesting question. What is nice, and this, we can talk about academic freedom, and this is one I value. I am just a university professor. I can just tell you what is happening. You may choose not to believe me, but we just provide the data. But yes, that has come up to our meetings. Certainly, there is a lot of uncertainty at the Environmental Protection Agency that does the regulation. I called my friends at EPA, and they are sad. I mean, they have all these cap and trade programs. My understanding is our program will continue at least through the EPA. They want to continue funding the data because I am safe. All I do is report the data. But certainly we have discussed that we need to, there have been some discussion of funding cuts that will directly close our stations because we do not fund them. They are individually funded. They pay our university on an individual grant basis. The money is terrible to manage, but we could lose the stations and then we simply won't know the impact, and that is what's the most scary thing, yeah. Because, as I think we said discussion yesterday, if you don't measure, you have no problem.
A good political question, Oscar.
Did I respond in an appropriate
Chris,
way?
I hope that when you get back to the United States, you will continue with your job. Okay, another question, Abraham.
Thank you very much. Nice presentation as well.
Thank you.
I just want to comment, probably it's now the numbers it's important. In terms of scientific, or probably Oscar mentioned about the questions, about the objectives of the network is one of the challenges most important. And I want to know, or probably you can give us an experience about, if you see the numbers of Mexico in terms of the position, we only have Mexico City, and
Yes.
that's it. It's a terrible action. In terms of we want to grow the national network, you mentioned the synergies between a lot of people or institutions that are involved in these actions.
Yes.
How is the cost to implement something like in this? Of course, the United States, the coverage is biggest one. How is the cost per unit in sampling?
Yes.
Is one of the questions, because I think if we want to make something like this one, we need to put in mind that it's a cost.
Yes.
And probably this is the things we need to do first if we want to create a national network.
Yes.
Second, it's with these numbers, in terms of scientific questions, but as well in terms of impacts. For example, if you can mention now to the agricultural zones or these states, you are increasing the ammonia, so you need to decrease something because you are impacting increment of nitrogen. So probably you have eutrophication in these areas. So how is just connections with the people and the decision makers, for example?
Yes, and thank you for the question. And in the interest of time, I kept it limited, but certainly nitrogen deposition is of keen. So I'm going to answer that first, and I'll get back to cost. You asked that last. So our data are used to integrate to find total deposition of nitrogen in the United States. I had some maps, but in the interest of time, I thought it would be better to keep a simple discussion and we could have questions. But there is an effort to integrate wet deposition and dry deposition to look at total deposition of nitrogen. And that's used, the term is critical loads. So for each sensitive ecosystem or national park, we can decide how much nitrogen can it receive without having adverse impacts. Two studies come to mind. There's Chesapeake Bay here that is a source of water, and so we have some keen studies to look at nitrogen deposition there. And then Rocky Mountain National Park in Colorado, because of the industry in the area, is causing nitrogen impacts on the park. And specifically, when you have a natural area and you add nitrogen, it's like fertilizing your field. So you have invasive species, non-native species can thrive, your native species can fail. So nitrogen is certainly of concern, and that's why the ammonia is of keen concern. Actually, that was the topic of my doctoral dissertation, as I talked about how acid rain decreasing has affected nitrogen, and it has to do with the balance of sulfur and nitrogen in the atmosphere, the acidifying and the reducing atmosphere. That's a whole another hour talk. So I think I've addressed the nitrogen, and I'll talk about cost next. We operate on an economy of scale. My laboratory has about 22 people. We have 20 full-time equivalent staff. So 20, when you pay the pay, it's about 20. Our total budget for our laboratory is 1.2 million US, which isn't much. I mean, that covers, that's just from the large network, the National Trends Network. That covers about 12,000 samples And we actually have a per sample basis. So if you or Dr. Sosa want to start a site, you pay me $82 a sample. So we charge $82 a week. And that is all inclusive of we wash the supplies, we ship them to you, you sample, you report on the field form, you send it back to us, we analyze it, and send you a report. That is a lot of work for $82 US. I know it's more than Mexico, but we can only survive through economy of scale. So that is because we have 12,000 samples a year, but that's not much money. That's a lot of analysis for not much money. It's all inclusive. And because it's a cooperative research program, everybody pays the same. So even to Mexico, I can only charge you $82. Everybody, Alaska, I lose money on some of my Canadian sites, but I have to accept them because as a not-for-profit government organization, we have to cover costs. Does that address your direct costs? I mean, it's published rates. It's a per sample basis. There is no negotiated. Everybody knows the cost. It's public information. Ammonia monitoring network, I think, is $72. And again, all-inclusive. We pay postage, all-inclusive.
Please take note that talk with Dr. Panorama. Okay.
Here,
Another question?
Here.
Please.
Thank you. Thanks for the presentation. I was wondering, in general, how you seem to get your fluxes, your mass fluxes for either any of those species by having rain rates, right? Is that?
Yes. Explicitly, the wet deposition, if you do the derivation, it's the chemical concentration multiplied by the amount of precipitation, and you have to do units adjustment. But yes, that's how you get the mass flux for wet deposition, yes.
We have some concerns about the quality of the data, even in the US, for precipitation rates. So how do you deal with those things?
Well, for one, we operate our own network. So we have our own rain gauges, which we verify calibration. We also verify how much water is collected by the collector and compare it against the rain gauge. And we have some telemetry. So when the collector opens, it tells the rain gauge, so we have a full signal. So we essentially, for the quality, we operate our own network.
All right.
And quality
So,
assure it.
Have you ever compared with the national network? I mean,
And actually, that's what this is. So we don't have thousands of sites out here, but we rely on a computer model. So this is actually what's called PRISM. It's put out by the University of Oregon. But we do ground truth our data against National Weather Service. But the primary quality is we simply operate our own network.
Right.
And we send a team out to calibrate the gauges.
Thank you.
¿Más preguntas, por favor? Adelante.
Do you have plans to consider the number concentration in the future in your network?
You mean predictive, like what mañana, so what it looks like in future years. You know, what's interesting, our primary mission of our program is simply to provide high-quality data in a cost-efficient manner. So somehow we've balanced cost-effective with high quality with what's fast, cheap, or good. We've got those. I'm coming to your question, but our primary mission is simply to provide data. We've done trend analysis to look in the back, and then the reason the organizations look to us is they're the ones that do the future casting. So it is not within our mission to do future casting. We only do trend analysis and quality assurance studies. I don't think I've answered your question, but in short answer, no, we don't do forecasting, like weather, no. There are some groups, however, that of attempting to integrate it with, you know, CMAC, the model, the air quality model. There is a forecasting module in it, and they've used our data to pull it in to correct it, if you will. So we don't do that, but there are groups using the CMAC model. It's a community model for air quality.
¿Más preguntas, por favor? I have one. Can you help me with the slide when you present the emissions trends for SO2 and nitrous oxides, please?
Maybe can our friends in the back, can they, because I have to go back 100 slides because,
Okay.
well, we can, I might be able to go quickly. Look quickly.
My question is about the strategies that reduce the emission of sulfur dioxide and nitrous oxides in the United States.
This one.
The other. Here.
Okay.
It's an excellent strategies because the reduction in the emission is clear. You talk about the power plants
Yes.
That is stationary sources. What about in the case of mobile sources?
Yes. And what's interesting, and again, I try to keep the message pretty simple today, and I appreciate the discussion. Sulfur dioxide in the United States what was called cap and trade, so literally cap, so they put a limit on it, and you have your big power plant, I have my little one, I can sell. You know, you want to be a big emitter, I want to be a little emitter. So that is actually how they controlled sulfur dioxide. Sulfur dioxide is very straightforward. You can do the math. Perhaps you teach this in your classes. You know your fuel. You know how much sulfur is in it. You can calculate. This is very straightforward. The problem is the government wants to make everything look like sulfur, like carbon dioxide. So this was very easy, and it's primarily power plants. Nitrogen dioxide, instead of just saying you can only emit so much and you control the amount of fuel you burn, they defined control technology, and the term was best available control technology. So they implemented that, and it simply said power plants had to implement this control technology to mitigate or lower their NO2 emissions, and that's where the vehicles came in. That's where we had the catalytic converters in our car to control nitrogen dioxides, but sulfur was an absolute. They just said, emit no more, it's easy, you just don't burn the fuel. Nitrogen dioxide, well, as we know from our German friends, is not quite as simple to control. I don't think I answered your question,
Yes,
but certainly it talks about diesel emission fuel, DEF, and you know, it's a complicated answer because it has to do with the combustion, and I know your students learn this, to learn how the formation of nitrogen oxides. So it was simply control technology what the US defined, and the Germans can tell us that doesn't always work.
Please.
Mercury. What's interesting is most of the heavy mercury emissions in the United States were actually controlled before we started our network. So our network was started in 1995, and many of the worst emissions of mercury, like chloralkali, cement production, when we all go to heaven and they burn us, our teeth, you know, the crematorium emissions, that was all controlled prior to that. So now the regulation is a lot on a state level, but looking at mercury emissions from power plants. In the United States, we mostly controlled the hospital waste emissions and the industrial emissions. The big source, to the best of my knowledge, it remains the coal-fired power plants, and that's the focus on the regulations. I don't know if I answered your question or not. Okay.
¿Alguna otra pregunta? Bueno, si ya no tenemos más preguntas, vamos a agradecerle primero a todos ustedes su asistencia y a Chris que está aquí, y feliz cumpleaños. Thank you, Chris. I appreciate your